enabling data-driven development for autonomous driving at BMW. Here to give us more insight about how to deal with challenges of data in the automotive industry is Miha Pelko, data engineer at BMW, focused on big data for the company's autonomous driving division. Miha has had a rich experience as a consulting data scientist and data engineer in the automotive industry, and he holds a PhD in computational neuroscience from University of Edinburgh. And Miha, we can't wait for this one. The floor is yours.
Yet. Not yet, not yet. I'll need your applause later. Thank you very much for this introduction. Thank you to the organizer for the invitation. I'm delighted to be able to speak here. Well, there's not much I can still say about me, except for, every good talk starts with disclaimers. Big data, autonomous driving, two hypes. If you are coming here expecting to hear about the algorithms we're using in the car, you're going to be disappointed. You are more going to be hearing what's on the data engineering side. I'm going to give you about 3 minutes to leave the room in case that's what you want. There's other very good sessions around. And then after 3 minutes, we're going to ask organizers to lock the room, and then you're in for half an hour. So make up your mind. Second disclaimer, it's first time at this conference for me, and I've only arrived a couple of hours ago, so I've not have the best impression yet of who's around here, who are you guys here. So I'm going to ask you for a little interaction in the beginning to kind of better form the talk. I hate when presenters ask me to exercise, so I was thinking, like, what's the least amount of action I can require from you to get some information? And I thought clapping. I mean, that's what you get in, you expect to do anyway. So normally you do it at the end. I assume you have a certain budget of claps you want to do. Let's try to take them now in the beginning. Just you can then forget them for the end. Yeah, is that all right? Brilliant. So what I'm going to ask you to is I'm going to be asking you some questions, and if the answer to that question is yes, clap once, one time only. And if the answer is no, just don't do anything. Right? Is it clear? All right, that was more than what I expected. Very good, well spotted. But okay, let's start with some baseline. Are you human? Good, that's our baseline for everybody. Well, let's try that. Are you a robot? Couple of wise asses, or potentially robots? I'm not here to judge. But okay, let's start again. Are you a human? Almost the same as the first time. I wanted to check here the variance. So here's your data science plug, right? We had some variance in it, but otherwise our sensors are quite good. Then let's go for real now. Who of you here is a student? Oh, quite a lot. Who of you here is at a university but not a student? Okay, 0. Who of you here is working with data? Almost everybody. Who of you here is doing data science? Who of you is doing data engineering? All right, a little bit. Who of you knows what Hadoop is? Awesome. Who of you knows what Spark is? Who of you has worked with Spark? Who of you has worked with Hadoop? Okay, good. I have a good baseline then. So I think the talk is quite all right for you guys. Because what we want to talk about, or what I want to talk about here today is, well, why autonomous driving needs data in the first place, why it needs a lot of data, we think, and also, how we now enable our developers with that data, specifically at BMW and our division. We're going to go for a little bit of a deep dive, and that's why I was asking all these questions in the beginning on the data journey as it's going from the cars to the Hadoop cluster and is being pre-processed so that the data can be used. So that's kind of the agenda for today. 3 minutes have passed. Okay, if you stayed in, stay in. Quickly, very quickly, you've probably seen something similar to this before. That's sort of a chart describing autonomous driving as it is being developed, sort of from a point where there is no autonomous driving in a car to a point where, well, you get some assistance, you have this assisted driving, to partially automated, highly automated, fully automated, and finally autonomous driving. So the first message here is the journey to full autonomy is incremental, and that's where we're going towards. And we're about here now in a moment in the world, not just with us. We're obviously trying to get here, right? So that's kind of clear. Now, and I argue that to do this, we could still get around by doing things with certain amount of data, but not a lot of data. And to get to the end, we'll need a lot of data. And the reason there is, I know I haven't asked that question. Well, I presume not all of you have done robotics programming before, but typically, autonomous car being a robot, the way you program it, you give it some sort of rules how to behave. If you are heading towards a wall, if you're that close to the wall, if the speed is like that, start braking. Yeah? This type of rules. And with these rules, you're kind of describing the behavior of your system, and that's how you're developing your autonomy. However, as soon as we go full autonomy, we go urban, we go to the city where there's so many things happening around you, all of a sudden, it's practically impossible to describe all these inputs coming in to your decision in this type of descriptive rule-based manner. It's also not always even clear which of those inputs are relevant for the decisions that you need to be making. And in order to have that ability to know what's important, to know which situations you will see, to kind of reduce this huge dimensionality that you see, right? I mean, all these inputs are leading to this combinatorial explosion, data science. And all of that is, you need a lot of data to kind of sculpture that out. And that's hopefully one way of showing you why do we need a lot of data. The other way of showing it is this image here, which is not just a picture of the cutest child ever. It's also a picture of how humans normally learn how to drive. So this is a driving school car. What I would argue is we really start learning already from this perspective here, right? So school of life, as you start living, you're starting to learn even how to drive. You're starting to learn how to observe environment, how to make sense of it. But even in the traffic, you start observing how the traffic behaves, how different objects in the traffic behave and whatnot. So it's, in a sense, and obviously, taking in a lot of data as you're doing it. And that really is, right? So this is something what we, I think, should imitate when we're going into development of autonomous vehicles as well. Imitating about how humans learn. Speaking of which, as an example of human eye and the brain, there's some estimations. Obviously, all these things are not super clearly measured because we're talking about biological systems. But there's estimation about the information transfer coming from the bulb of the eye to a brain going at about 1 megabyte of information per second, which then over the 18 years before you start learning how to drive officially, you get into petabyte regimes quite quickly. And that's just the eye. That's not including the other sensors, and it's not including the fact that a lot of processing happens here already. So the amount of data, you can imagine, right, 1 megabyte, that's like 1 image per second. We're better than that, right? So a lot of it's happening here already, and that's not even captured in here. So humans, as we're learning, we are absorbing a lot of data. Cars, already now, and that's level 2 autonomy, right? So it's quite a beginning. So ADAS systems, autonomous driving assistance systems, they already pack quite a lot of sensors. I think here we have 23 sensors on the BMW Series 5, which is already out there. So that's already giving us a decent amount of data. Now, I can't quite show you the exact sensor setup for the current development fleet, but what I can tell you is that we are talking about several terabytes produced by a single car per hour, right? So there's cameras, radars, other sensor systems, bringing in quite a lot of data. So if you start to do some calculations, you have 40 vehicles that are doing collection of that data, 8 hours per day, several terabytes per hour, you're quickly in the petabyte regime here as well. And that's where we're hoping will help us get further. Data development, so this is, we need a lot of data. Now, how do we actually use it? You start here, you start doing test drives with human drivers in those vehicles so that you start collecting all this data. That data, and then set several terabytes per hour, are getting ingested into the data center. Now, as we'll see later in the talk, it's not completely straightforward, and specifically this data here is not quite usable yet, so you need to do some pre-processing, organizing it, structuring it, so that you can get some better data set, better forms of the data that people can actually work on. You get those target data sets that you can either machine learning train on or use for a more traditional robotics development, in any case, to develop the algorithms that will finally go into the car, which is going to go further out on the street, collect more data, and so on. So you have this typical iteration cycle of development of the autonomy. Now, this is a bit too slow. Now, the battle for building the autonomous cars is a fast one, so you need to speed it up. So the way you do it, you introduce a little shortcut here. And instead of actually running those algorithms in the cars being run around, which is the biggest time-consuming factor here, you try to do this in software. And for that, what you need to do is you need to bring the software that's running in the car onto the data center. And while I'm not going to talk much about this today, I can tell you this is one of the problems, one of the challenges that we are doing as well in our team. So one of it that I will talk about more is how to kind of bring the data in and organize it. The other one is now how to run the algorithms inside a car that's normally inside a car on those inside the data center. Right? And this basically kind of gives you then this speed up loop that can be done on a daily basis or even an hourly basis instead of weekly. That would be normally happening going around the full circle. All right. Now, see, for me as a data engineer in our group, my customers are actually the developers of these algorithms. So this is for me now the customer here, and the customer, the developer is thinking, right? I want to develop a function that of driving on a roundabout with pedestrians. So for that, he wants to have some sample data. He wants to see what are the scenarios that are really happening outside in the world. We've collected quite a lot of data already. Let's find that data, right? So that's the one thing is find existing relevant scenarios. Alternative is, yeah, you can always order to drive around or go and drive yourself to collect those scenarios. But I mean, since we've been collecting terabytes, petabytes, we might also just want to search through that. So you need to make sure that your data is searchable. You need to be able to export some of the data. So sometimes still the best way to quickly iterate is to get some data locally, do some development there locally, and then push it onto the data center. So that's one thing you need to be able to offer. You need to be able to train those models, either again locally or in the data center, run the new algorithms on the data, that's what we talked before, and then calculate different KPIs of how is the new algorithm now performing on the data that we had before. So you can compare, are you actually going better or are you regressing? So these are kind of the tasks that we have to do. Some of the missing things that are a bit more data science is we need to do an analytics of the actual scenarios, extracting out the scenarios from the data sets, doing the test coverage, trying to figure out what are the really important scenarios that we need to cover a lot, what are the ones that happen less rarely and so on, less regularly, sorry, and so on. So those are then more data science type things that we need to do as well. And now we go into the deep dive, right? So we'll talk about how we get those things ready so that our customers are happy. So the data journey from the cars to the developers, essentially. And there we're using Hadoop. And then most of you, I think, have clapped that you know Hadoop at least, which is very good. So I'm not going to spend much time on describing what it is. And for the rest, tough luck. Hopefully you pick it up as we go along. Start with some concepts. So this is how our data normally looks like before it's being logged. So this is now still data in the car. What's happening on the buses in the car, communication buses, there's a lot of messages being passed. Here I'm presenting a specific stream. That's a type of data. So in this case, for example, the image stream, the video stream coming from a single camera will look a bit like that. It will be sending a lot of messages that together, like a couple of them, will form an object. In the case of the image stream, that's an image. So in the communication bus in the car, you don't have images flying around complete. What you have is typically you have messages that are split parts of the image that are flying in. So this is what we're talking about when we mean messages. The object is now the full frame, the full image, and stream simply refers to a certain type of data coming in. Now, the loggers in the cars have a quite a difficult job because, just pushing down those terabytes of data per hour on the disks locally is already a challenging task. So they can't really be smart, unfortunately, which means that all they can really do is package those messages into files, not caring whether they split objects. they don't know which object the message refers to. They just push it into the file. So that's what we get. We get several files with those streams where the things can be fragmented around. And that's one of the problems that we have to be solving later on. So now to finally put it together, we have a car that's logging things. There's a logger inside. Logger has an SSD or SSD that so solid state drive where the files are being logged on. Each file set can include several streams, and the messages are just coming in there as they are. And although here they look very ordered, there can be some mismatch in the ordering of those messages as well, which kind of adds on to the list of tasks we need to do later on. And typically we'll have several streams collected within a single file and not just one as shown here. All right. So now we're ingesting data to the cluster. The way this happens is a driver, having been driven in a car, having a SSD with the data, goes out, goes to what we call a copy station, put an SSD in, presses a button, and the data gets copied into ingest servers. These are somehow the buffer storage places that then allow us to quickly dump the data from the SSD so that the SSDs can go back into the car and be reused. While in the background, the data is going from those ingested, from this buffer into the HDFS. HDFS here stands for Hadoop Distributed File System. That, for me, is the main Hadoop ingredient, at least is the main one that we use. Is a distributed file system. One sentence, you have a file system that's not just on one server, it's on several servers, and the data is replicated. So in our case, typically 3 times, so that the files will actually end up at on several different, same file will end up on several different servers copied. And that is important for 2 reasons. One is obvious redundancy. So if your disk fails on one server, or if one server fails, or even a rack fails, you still have your data. And the other one, and that's the important one for this talk, is it enables to process the data locally. So it enables a better coverage for data locality. Data locality here meaning that the data that is being processed by a certain CPU is actually residing on the same server where the CPU is, right? So now the more replication you have, the better chances are that if you're telling to your server, handle the data, that the data is actually at the server level. And Hadoop, or Yarn in this case, is letting you do this a bit smartly. So it will typically schedule your jobs on the data nodes that host the data where you're on. And to help Yarn, in our case, we've set, really for the Hadoop nerds, we've set the block size equal to the typical file size, which in our case, I haven't mentioned yet, is 2 gigabytes. And that's not a default Hadoop setting. The block size essentially is the amount of block, the block that gets replicated around. So in our case, that's exactly the file. So that makes it simple, but it also makes it efficient for this data local processing. So in order to have that done, I haven't mentioned before, but those files are specific files called MDF4 files. It's an automotive closed standard. But they are there. They're not so friendly to work with Hadoop. So we had to write something called the MDF4 input format. And since we have our block size the same size as our file size, we typically, once we use this input format with Spark, we'll get to Spark soon, we get a data frame. So that's like pandas or R. We have data frames, but they're distributed data frames. So your data frame residing on several servers in the cluster, where the partitions of that data frame always contain a single file's worth of message. And that's important, as we'll see later, because it enables better data locality. So without going too deep into the details of how this implementation of MDF4 input formatter, it's quite a naive one in that case, but it works really well. Now to the problem at hand, right? So we said the messages coming into the server are quite messy. Messy in the sense that they can be scrambled around, different types of messages come in the same place. And what you can have is you can have messages corresponding to the same objects, like a blue color here, split between 2 files. So we need to stitch those things together in order for our developers to actually do something with it, because they can't do anything with it as a single message. For this is a bit of a algorithm that we do there in order to stitch it together in Spark efficiently, that there's as few shuffling happening as possible. Shuffling in this case is basically data having to go from one server to another. Once you have a really big data, that's what you want to avoid. You want to avoid data being passed around because your data, there's a lot of it, and you want to bring your algorithm to the data rather than the other way around. So what we do is we first patch things within the certain partition, so all the messages that were within the same file, and then that was the first step, and then the next step, we just take the ones that were not patchable or that were not defragmentable within that file, send them around, shuffle them, that's the unavoidable shuffle, and we patch them then later on in different partitions. Finally, we union those things together, so we get, again, now a data frame of defragmented messages. So we have now objects, right, that we had before. We have images, finally. Now, one final thing to do once we have those objects is, when they're images, it's quite easy. It's a binary array that's an image, but often these things is more complex data, such as data coming from the radar or from the lidar, and it's basically a byte array that you need to somehow deserialize in order to make it understandable for people. So that's what we call decoding, the process of decoding, and that decoding is very specific to each data type. So, for example, here we have image data, radar data, and then speed data, that's our GPS data, for example, which we then map, decode, and put into RDDs, separate RDDs of a separate data types. Finally, those RDDs stands for resilient distributed data sets, and it's a Spark data container. Now those then finally get saved into ORC files or Parquet files, so files with a columnar data storage. If you're not familiar with it, it's basically files that play well with Hadoop and Spark and are quickly analyzable because they're optimized for such things. So finally, we've gotten from our sort of a bit of a messy data into such structure which we can then offer to the developers. So now you have your data that has been pre-processed, structured, has been put into different buckets. There's some other things happening under the hood, such as time synchronization that I didn't mention yet. But finally, this is the things that people can actually finally work with. So we have happy developers, hopefully. 3 more minutes, so I can go a bit further from what we had so far. So that was the main circle. There's a little bit of a sidestep happening here as well. So even though there's a lot of data, and big data is good, and there's a lot of it, it's not enough sometimes. What you can never really observe everything that there is outside. So we try to imagine it. So what we do as well is, well, we do scenario extractions from the data, and then we manipulate that a bit. So that, you know, if you had a situation where there was a car taking over another car with a speed of 120 kilometers per hour, well, you can also try to create a simulation of that car now overtaking your car with a speed of 130 kilometers per hour, and all the rest in between. And that might be relevant for your algorithms. Specifically, if we're talking about it here, basically what I'm trying to say here is, well, imagine this is now the full data set, this combinatorial explosion of every scenario that I was mentioning before. In this case, only 2 dimensions, so that we can actually see it. Number of pedestrians and vehicle speed. We only observe a number of such scenarios, specifically. Now, what we want to do is we want to cover all this space to test it. So then you need to start imagining things around. And that's basically what we're doing in that step there. I still have it, where we go extracting the scenarios, combinatorial boost of scenarios, so we perturb things a little bit. You need to feed in the synthetic data, sometimes from the sensors. And then you get yet more data that you can test your algorithms on. And hopefully then make it even more safe, as what the initial quote was on the slide here. All right, we're getting close to the question time. Note from the sponsors. We have a really nice place. We have a lot of data. We have cars. It's good. We're growing still. So I'm hoping you're interested and will find me around for details. I'm here until lunchtime. Yeah, and then just humor me for one little thing. It's sponsors. I want to ask you to repeat the beginning exercise and answer the following question. I'm interested at working at BMW. Awesome. Great. Also, now I have images of all the people who have clapped, so I'll be hunting you around. And if I don't, please come to me and talk about those things, the opportunities we have. Thanks.
Thank you. Thank you, Miha. We received a lot of questions. Unfortunately, we don't have the time to go through all of them. Question number one, what would you think is the importance of pre-processed high-definition maps for autonomous vehicles compared to that data coming from onboard sensors in real time?
That's a good one. We haven't even started talking about it, but yes, there are maps in there as well. I think they are important. I think, basically it's a really hard problem. So all information you can bring in, the better. Then you're hitting some limits with how much computation you can do, but typically all information you can get, the better. HD maps are a part of that information. And are also a bit of a reason why I think that autonomous driving will start on a smaller subsets of the world, because those are then typically, HD maps are expensive and hard to do.
So question number two, with the eye analogy, how much data is already being filtered before being sent to the car, from the car to the data center? Which kind of data and how?
Wow, that's detailed. We try to not filter anything out. So we try to get as much as possible. I can't go completely into the details, but the idea is as much as you can get out, try to get it out, because you never know what you need. Now, how much of that is then actually used in the development of algorithms, it's a different story, but at least we try to get all of it out. That's where the terabytes are coming from.
What is your language of choice for Spark?
Holy crap. Scala. You can do some PySpark, but typically if you come with us, you'll be going right Scala, because it's more efficient.
According to the Stack Overflow, Spark and Hadoop are some of the most hated technologies. What do you think is the reason?
JVM, memory overflow errors. I don't know. I can't say. I kind of like it.
What is a similarity or a difference with NVIDIA's autonomous car, Day 2 data generation? How do you plan to handle flow of drivers' behavioral cloning?
Sorry, can you repeat that one?
So what's similarity or a difference with NVIDIA autonomous car data generation?
Not familiar with it.
You're not familiar with it? Do you process all data locally or in some other way?
Locally, well, as I was saying, we try to do as much of a data local processing here. And it's not always possible because the data is being split around.
This is an interesting one. In case of a crash, who would be responsible? You, the AI, the car, or the driver?
Don't ask the data engineer.
You're washing your hands.
We test our code. That's the best I can give you at the moment.
Can you run the data produced by the cars in a simulator?
Not me personally, but we use simulation as well, as was mentioned in the talk, yeah.
How do you solve the bandwidth problem with transferring data from remote locations?
SSDs, physical transfer rather than over the air, typically.
Are you considering public cloud?
Not allowed to answer.
How long do you keep the data after every analysis in the car, and do you reprocess it?
Not sure I'm allowed to answer that one either, but in general, as long as you can, but there's a limit to how much data you can store.
I will skip the similar questions then. When will we have fully autonomous cars?
Yeah. Don't ask the data engineers.
Do you delete your data after a certain period?
I think we had that one already. If it's possible not to, no, but sometimes you have to.
And could you explain what the machine learning algorithm consists of?
Sorry, consists of?
Yeah.
It's an ongoing process. I'm not directly involved in it anyway, but it's not like it's fixed.
Do you ever copy the data to relational storage like SQL Server?
Rarely. It's too much of it.
Why?
So we were mostly working with raw data. So there are cases, and there is that data that might go there, and it does. But for me personally, I mostly work on this big data technology, so not so much. Yeah.
You keep mentioning machine learning models, but you probably also use neural networks and AI to parse images for information.
Probably.
Have you used the car driving simulations to test developed AI? So it's similar.
Was hopefully answered.
Okay.
Yep.
That's all. Thank you very much. Before you leave, I would like to give you this certificate
Oh,
as a thanks from the organizers of the conference.
thanks. Okay.
Thank you very much.
Thank you.